Ohayou gozaimasu. Thank you for the invitation to speak at this conference sponsored by the IPMU. Scott just told you what the title is, so I won't repeat it. And part of this talk is a review of old things, going way back, and also some foundational material in a paper I wrote with Davide Gaiato and Edward Witten, which I'll refer to as GMW, Foundational Material for Categorification of Wall Crossing. The new things are mostly work that I've done with Ahsan Khan, a graduate student at Rutgers, who will be a postdoc at the Institute for Advanced Study in September. And at the end of the talk, I'd like to report on some ongoing discussions with Ahsan and Davide Gaiato and Fei Yan, Fei is a postdoc at Rutgers, a very good postdoc, and is looking for a job. And those current discussions were in the context of some larger discussions that also involved non-trivial input from Andy Kneitzke and Tudor Domofta. So here's the outline of the talk, and the organizers asked me to summarize the whole talk at the beginning. So ordinarily I wouldn't walk through the outline so slowly, but I will now. So the first part of the talk, I'm going to explain how simple considerations of supersymmetric quantum mechanics lead to natural and standard constructions in homological algebra. And then I will apply those ideas to 1+ one-dimensional quantum field theory, namely Landau-Ginzburg models with 2, 2 supersymmetry. And then in order to categorify, I'll review some aspects of wall crossing in that section. And then to categorify the wall crossing formulas, the first step is to think about the categories of branes, or the A-infinity algebras of branes and their local operators. And that will lead to a description of categorical wall crossing, the paper I wrote with Ahsan last October. And then I'll talk a little bit about the generalization to the case with twisted masses, which is the work we're doing now. And at the end, I'll explain an interesting relation to indices of three-dimensional supersymmetric quantum field theories. So with that summary, let's get going. So first, supersymmetric quantum mechanics and homological algebra. Well, this goes back to Witten in 1982. To formulate a supersymmetric quantum mechanics, we choose a Riemannian manifold M and a closed one-form alpha on it. Now, because alpha is closed, locally alpha is dH, where H is a real-valued functional, a real-valued function on M, which is the traditional superpotential of superquantum mechanics. But importantly for this talk, H need not be single-valued. Only the one-form alpha needs to be single-valued. In other words, alpha need not be exact. I'll call alpha the super one form. I hope that terminology doesn't cause confusion. So in superquantum mechanics, we have a field which maps time to the Riemannian manifold, and this is the bosonic part of the Lagrangian. And with this kind of Lagrangian, the classical vacua are the zeros of the potential, which are the zeros of the one-form alpha. I'll call those critical points. And we'll assume that they are separated critical points, isolated critical points, and that the mass matrix, the matrix of second derivatives at those critical points, is invertible. So in quantum mechanics, for each of those classical vacua, those critical points, there's an approximate quantum vacua. We could write it as psi of phi I. And you can calculate its fermion number. And it's 1/2 of the difference between the number of negative and positive eigenvalues of the mass matrix. Now, the approximate vacua are not exact vacua because of instanton effects. The instanton equation is this first-order flow equation in Euclidean time tau. And we can use the instantons to define an operator Q on the approximate ground states. So we define Q on a ground state associated with a critical point phi I to be the sum over approximate ground states with fermion number 1 larger, weighting that by the number of instantons that go from phi I to phi j. And then by studying the moduli space of solutions to this flow equation, you can prove that these countings of instantons satisfy a quadratic equation, which I've written here, which means the q squared is 0, which means you can form the cohomology of the space of approximate ground states. And Witten's claim was that this is the space of exact ground states. These are the BPS states, if you like. That shows you how superquantum mechanics naturally leads to the notion of a chain complex. In general, a chain complex is a triple of a vector space, V, and two linear operators, F and Q on V, where F is diagonalizable with a spectrum which is a Z-torsor, and Q raises the F quantum number by 1, and Q squares to 0. So in supersymmetric quantum mechanics, the vector space V is the span of the approximate ground states associated with the critical points. F is the fermion number, and Q is the supersymmetry operator. So in math, the supersymmetry operator is usually called the differential, and so I'll use those terms interchangeably. So in this context, I'll call the resulting complex the MSW complex for Morse, Smale, and Witten. And the MSW complex depends on this data of the Riemannian manifold M, the Riemannian metric, and the one form alpha, the closed one form alpha. And the exact ground states have the geometrical interpretation as the cohomology with respect to the flat connection D plus alpha. Now, we can talk about homotopies of this data. We can consider a continuous family of metrics and one forms alpha with control parameter S. And we can ask, how does the MSW complex change? So we can define a linear operator from the MSW complex at control parameter S1 to the MSW complex at control parameter S2 by again studying the same kind of instanton flow equation. And we define the operator to say that the approximate ground state for control parameter S1 is the sum over all approximate ground states for control parameter S2 with the same fermion number, again weighted by the numbers of instantons. So by definition, this operator commutes with fermion number, and then again by studying the moduli space of solutions to this flow equation, we see that U commutes with the supersymmetry operator. So in this way, superquantum mechanics naturally leads to the notion of a chain map. In general, a map between chain complexes, C1 and C2, is a linear map between the vector spaces that commutes with the fermion number and the supersymmetry or the differential. So we learned that under continuous deformation of metric and super one form, the MSW complex changes by a chain map. But actually, it's a very special kind of chain map. It's what's called a homotopy equivalence of chain complexes. So you see we have paths of data, but we could consider homotopies of paths of data. In other words, continuous maps from the rectangle into the space of metrics and the space of suitable alphas. And we fix the boundary conditions, so we have fixed data at s equals 0 and 1. So the path at u equals 0 gives one chain map, and the path at u equals 1 gives another chain map. And you can show that the difference of these chain maps is q exact in the sense of this equation. And to show that, you again consider the flow equation, and you define the operator E, which now maps an approximate ground state of one fermion number to the sum over all the approximate ground states of one lower fermion number, again weighted by the number of instantons. And again, by studying the moduli space of solutions to the flow equation, you can prove this equation that the difference of the chain maps is q exact. So in general, if we have two chain maps between chain complexes C1 and C2, we say they are homotopic if there's a fermion number -1 map, E, from V1 to V2, such that the difference of the chain maps is q exact in this sense. Now, if there are chain maps going both ways, F and G, such that the compositions going both ways is homotopic to the identity chain map, we say that the chain complexes C1 and C2 are homotopy equivalent. So homotopy equivalence of chain complexes will be a very important notion in what I'm going to say in this talk. In superquantum mechanics, running the control parameter S backwards is enough to show that U is a homotopy equivalence. In general, a chain map between two chain complexes induces a linear map on the cohomology spaces. And if F is a homotopy equivalence, then F hat is an isomorphism. So in this way, one can show that the cohomology with respect to the flat connection is a homotopy invariant of both the manifold and the one form alpha. So now let's apply these ideas to two-dimensional 2,2 Landau-Ginzburg models. So to define a Landau-Ginzburg model, we need a Kähler manifold, capital Latin X, and its Kähler metric, Gij bar. And we need a 1,0 form, alpha, on X, which is holomorphic. Now locally, alpha is the derivative of a locally holomorphic function, capital W, commonly called the superpotential, on X. But we will be considering multi-valued W's. That's okay as long as alpha is single-valued, because the action is, or at least the bosonic part of the action is written here, and the entire action only uses alpha and not W. So the theory makes sense when alpha is not exact. Now, here I've written the action of a 1 + 1 dimensional quantum field theory with spatial domain D. If the spatial domain is the real line, then we can speak of Poincare invariant vacua, and those are the constant field configurations which sit at the zeros of this alpha. Later on, we'll apply this to branes where the spatial domain is a half-line. It's very useful to think of this Landau-Ginzburg model as a one-dimensional superquantum mechanics. We consider the superquantum mechanics with a target space capital calligraphic X, which is the space of all maps phi from the spatial domain D to capital Latin X. I'll try and distinguish quantities associated with capital Latin X by blue and capital calligraphic X, the superquantum mechanics, with red. So you see the Kähler metric on capital Latin X, Gij bar, induces a Kähler metric on capital calligraphic X by this equation here. And similarly, the one form alpha of type 1,0 on capital Latin X induces a super one form alpha tilde on capital calligraphic X by this equation. In this equation, omega is the Kähler two form on capital Latin X. We can pull it back by phi, integrate over the one manifold D, and get a one form on the space of maps phi from D to X. Similarly, we can pair alpha I of phi with delta phi. Delta phi is the standard notation for the cotangent vector on the space capital calligraphic X. We can pair those, multiply by a phase, zeta inverse, take the real part, wedge with dx, and integrate over d to get a one form on capital calligraphic X. And it's then a very nice elementary exercise to show that the superquantum mechanics with capital calligraphic X and alpha tilde is the Landau-Ginzburg model with capital Latin X and alpha. As I said, in usual discussions, this alpha is not mentioned because we only work with a well-defined, globally defined, holomorphic Morse superpotential W. But if alpha has non-zero periods, the theory still makes sense, but there's no single-valued superpotential. This is what physicists mean when they say there are twisted masses. In this case, there exists a minimal abelian cover, pi, which goes from capital Latin X hat to X, such that if I pull back the one form alpha, it does become exact, and there's a globally well-defined superpotential capital W hat on capital X hat. The deck group for this covering is called capital gamma. It acts freely on capital X hat, and so we can also think of it as defining a subgroup of the homology, the first homology, of capital Latin X. So it's often convenient to consider the Landau-Ginzburg model upstairs, so to speak, and just work equivariantly with respect to capital gamma. The vacua of the Landau-Ginzburg model upstairs will be denoted V hat, and those are just the points phi hats of A, which are stationary points for capital W hat. And I'll abbreviate those vacua, phi hat A, phi hat B, simply by A and B, and write the free gamma action on V hat as A shifts to A plus gamma. So for example, the critical values of capital W hat shift under A plus gamma to W hat of A plus the period of alpha over the homology class gamma. As a very simple example, we consider the mirror of the free chiral field. The Landau-Ginzburg model in that mirror has target space capital X, which is the punctured complex plane. The covering space, of course, is X hat equals the complex plane, and the covering map is the exponential map, and the deck group is just Z. So if there's a mass parameter m, then the super 1 form is m over phi minus 1 d phi. It's closed, but not exact. But if we pull it back to x hat, it does become exact. Now the set of vacua, there's only one vacuum, only one zero of this super 1 form at phi naught equals m, and that pulls back to the vacua v hat, which are labeled by an integer a. The critical values of the superpotential upstairs have these values, and you can see manifestly that if I shift a by n, then w hat of a plus n is w hat of a plus 2 pi I mn, where m is the twisted mass and n is an integer. Other examples which are notable is the mirror of CP1 model. This was recently discussed in the GMW framework in the paper of Dima Galhov that Dima spoke about at this conference, and related results are in the paper that I'm writing with Ahsan Khan, and which will appear. Similar models have come up in discussions of knot homology from the physical point of view using Landau-Ginzburg models, and those have appeared in the papers which I've listed here. And they are related to what Mina Aganagic spoke about. Now later on in the talk, I'll also talk about another example, which I like to call the Chern-Simons Landau-Ginzburg theory. So here GC is a complex Lie group, M3 is a Riemannian 3-manifold, and that canonically defines a Landau-Ginzburg model, which I'll call LG of GC and M3. Where now capital Latin X is the infinite dimensional space of complex GC connections on the 3-manifold M3. The 1 form alpha of type 10 on capital Latin X is the push forward of the Pointryagin density along the 3-manifold M3 to give a 1 form on capital Latin X. This is D of the Chern-Simons action, and so the vacua of this Landau-Ginzburg model for the real line are just the flat GC connections. And we'll come back to this model at the end of the talk. Let's now return to the general Landau-Ginzburg model, possibly with twisted masses. In the super quantum mechanics point of view, the super quantum mechanics vacua are the zeros of the super 1 form alpha tilde. In Landau-Ginzburg language, those correspond to solutions of this differential equation in X, which I'll call the Zeta-soliton equation, and it will be absolutely crucial to everything I say from now on. So take a moment to look at the Zeta-soliton equation. The super quantum mechanics instanton flows correspond to solutions of this differential equation in the complex Euclidean plane, which is the zeta instanton equation and is a deformation of the Cauchy-Riemann equation. Now the MSW complex for this super quantum mechanics, in order to formulate it, I need to choose, so the stationary points are the solutions of the Zeta-soliton equation. To have a good MSW complex where we have good critical points, we have to choose boundary conditions on the field phi of x on the real line so that phi of x approaches the vacuum phi I at the left and phi j at the right. Then we can form the MSW complex, namely for each classical soliton phi ij of x, there's an approximate ground state in the quantum field theory, so psi is a functional of phi of the field phi of x. And the fermion number of this approximate ground state is given by a certain eta invariant, and the differential or supersymmetry operator counts zeta instantons. In the case with twisted masses, these MSW complexes have what's called a flavor charge. If we have a classical soliton, we can look at the image of the real line under the classical soliton, and that will be a path in capital Latin X from phi I to phi j. If we look at that path up to homology, we'll call that the charge little gamma sub ij. So it's the homology class of a path from phi I to phi j. And it lives in capital gamma ij, which is the space of all paths in X from phi I to phi j up to homology. Now this gamma ij is a gamma torsor. If gamma is a homology class on X, then we can add meaningfully gamma ij to gamma to get another path in X from capital phi I, from phi I, the vacuum phi I, the critical point phi I. I should not have said critical point. From the 0 of alpha phi I to the 0 of alpha phi j. Now Rij is graded by a gamma torsor, gamma ij, the gamma ij I just defined. So it has components. I'll write the components as capital R sub little gamma ij. The BPS index is associated with one of those components. We take the trace of -1 to the fermion number over that component. The central charge in that sector is then the integral of alpha along the chain going from phi I to phi j, little gamma ij, and it only depends on the homology class. This generalizes the very well-known formula in Landau-Ginzburg theory when a superpotential does exist, that Zij, the central charge, is just the difference of the critical values of the superpotential. But in this case, there's no superpotential, and one way to see that is that if we add gamma to gamma ij, then the central charge changes by the period of alpha around gamma. If we work on the cover, we discover something important. On the cover, there exists a superpotential, capital W hat. And there we choose boundary conditions phi hat A and phi hat B, which project to phi I and phi j, respectively. Now, famously, if we project a solution of this Zeta-soliton equation to the complex capital W hat plane, the solutions evolve along straight lines in the capital W hat plane, which are parallel to the phase I zeta. So in order for the left-hand side to meet the right-hand side, the phase has to be a very particular phase so that these two straight lines can meet, which means that R sub gamma ij is only non-zero when I zeta is parallel to the phase of the central charge, Z sub gamma ij. Now in the case with twisted masses, there's a qualitatively new feature. If upstairs B is A plus gamma, then because B and A are different when gamma is not zero, we can have non-trivial solitons. But downstairs, the projection of phi hat A and phi hat B is the same vacuum, is the same point phi I. So we can have boundary conditions where phi of x goes to phi I on the left and the right, and yet there are non-trivial solutions. You see, when there's a superpotential, the Zeta-soliton equation is a gradient flow equation. So in that case, when there's a superpotential downstairs on capital Latin X, the only solution with these boundary conditions is the constant field phi of x equals phi I. When there are twisted masses, that's not true. There are non-trivial periodic solitons. They carry non-trivial central charges given by the periods of alpha. And here in this equation, you might note that I'm identifying the space gamma II with the deck group gamma, or the homology group gamma. So RII is a fermion number times gamma graded complex. As we'll see later, the main new ingredient in categorified wall crossing with twisted masses involves Fock spaces constructed from the RIIs, similar to the halo picture of 4D wall crossing. Let's remember a little bit about wall crossing when alpha is exact, when there does exist a superpotential. So now we can continuously change the Kähler metric and the superpotential. And then as discovered a long time ago by Ciccati, Fenley, and Trilligator and Waffe, and Ciccati and Waffe, the BPS index, which only depends on ij, not gamma ij, is piecewise constant as a function of the control parameter s. But it can jump. That's very different from the finite dimensional situation in superquantum mechanics. You see, the mu ij can be thought of as just the Euler character of the MSW complex. If the superquantum mechanics has a finite dimensional target space, it can't jump. But we have capital calligraphic red x, which is infinite dimensional, and the Euler character can jump. The Ciccati-Waffe wall crossing formula tells us exactly how these BPS numbers jump. The categorified Ciccati-Waffe wall crossing formula aims to describe how the homotopy equivalence class of the MSW complex Rij jumps. Now when we have wall crossing with twisted masses, it's a little more elaborate. We have qualitatively different phenomena because we can have new kinds of walls. You see, if there's a wall in parameter space where the central charge with charge gamma ij is parallel to the charge gamma, then infinitely many walls go through each other. To see that, let's consider just two vacua, phi I and phi j, and the deck group is rank 1. Then you can have central charges that look like this in a half plane. Clearly, when z gamma ij becomes parallel to z gamma, an infinite number of BPS rays will cross through each other. In a recent paper of Garofalidis, Gu, and Marino, such a picture was called a peacock pattern, and I will come back and comment on the GGM paper at the end of the talk. Let's remember how the BPS indices jump in the case with twisted masses. That's called the 2D, 4D wall crossing formula. So notice that we can compose curves that go from phi I to phi j and phi j to phi k. And that defines a way of adding charges of type ij to charges of type jk to get charges of type ik. And indeed, the composition of curves is exactly the abelian group structure on gamma ii that allows us to identify it with the deck group gamma. Then we can define something called the vacuum groupoid algebra. For each charge little gamma ij, we introduce a variable, x of little gamma ij, with a multiplication law that says that the product of the x's is 0 if the paths do not compose, and if the paths do compose, the product of the x's is the x of the composed path. So now we can formulate something called the 2D, 4D spectrum generator, which is an element of this algebra. First, we introduce what are called S factors. For each charge gamma ij with I not equal to j, we introduce this simple expression. For each charge gamma in the deck group gamma, we introduce k sub gamma, which is a sum over the vacua downstairs, of a Fock space character times x sub ui, where ui is the additive identity in gamma ii. Then we choose a half plane in the complex plane, and we take a product over all charges, gamma ij and gamma, whose central charges lie in that half plane. We take the product of the S factors and the K factors, and we phase order the product. That is called the 2D 4D spectrum generator, and the 2D 4D wall crossing formula is simply the statement that as parameters vary, this S is invariant provided no BPS rays enter or leave the half plane. In general, that's all you can say about how the soliton degeneracies change. But in the case of only two vacua with a rank 1 deck group, you can say explicitly how the BPS how the BPS degeneracies jump across this wall. We formulate generating functions like this. For II type vacua, we take a product of Fock space characters. For IJ type vacua, we take a sum over all the charges of type ij, so we have gamma ij plus the multiples of gamma, weighted by x of gamma to the k. Those are the aij's. Then the similar generating functions on the other side of the wall are related to the original ones by these fairly elaborate formulas, but that solves the formula, the wall crossing constraint of the previous slide, and later on I'll give a categorical analog of that formula. So, how do we categorify these wall crossing formulas? The secret is to look at thimble branes and their local operators. So we're going to use the A infinity algebra or category of branes. The main idea is simply that the homotopy class of that category is an invariant of wall crossing. So for a brane, we choose a half plane. Excuse me. We choose a half plane, and in the pictures on the slides, I'll choose the right half plane. But in general, I could choose any half plane in the complex plane. I will choose the right half plane in my pictures. In this plane, we have a space, which is a half line ending at x equals x naught, and the brane is a boundary condition at x equals x naught on my Landau-Ginzburg theory. There's a special kind of brane called a Lefschetz thimble. We have a Lefschetz thimble associated with each Poincare invariant vacuum, phi I, for the Landau-Ginzburg model. The support of this brane is described by considering the possible values of phi at x naught so that there exists a solution of the Zeta-soliton equation so that as x goes to infinity, phi of x evolves to the vacuum phi I. You see, you can view the Zeta-soliton equation as a flow equation in X. And you can ask what boundary values at X naught will flow to the vacuum phi I. That defines a submanifold in capital Latin X. You can show that that submanifold is a Lagrangian subspace and provides a nice half supersymmetric boundary condition for the Landau-Ginzburg model, which preserves half the supersymmetry, this half, where we take this linear combination of supersymmetries. Notice everything depends on the phase zeta. As an example, supposing we have the simplest of all superpotentials, then the Zeta-soliton equation looks like this, and you can solve the equation very explicitly, and there are two branches of solutions. If you want the solution to evolve to phi equals 0, the critical point, as x goes to plus infinity, you need to choose the minus branch of solution. Then the phase of phi of x is fixed up to multiplication by a real line, by a real number. And so the image, the set of possible boundary conditions that flow to the critical value phi equals 0 as x goes to plus infinity, is this red straight line in the complex phi plane. Notice that if I had changed the half plane, so I chose the left half plane, then I would want the solutions which approach phi equals 0 as x goes to minus infinity. So then I would choose the plus branch of the solution of this equation, and I would get another Lagrangian brane. So the branes, the Lefschetz thimbles, and indeed the whole category of branes, depends on a choice of half plane. So now if we have branes, then we have boundary condition changing local operators between the branes. So we choose a half plane, H and C, and then we can consider the vector space, R hat sub ij, of local boundary condition changing operators between Lefschetz thimbles of type I and J of phase zeta. I'll picture those as these green squares. This R hat ij is a chain complex. In fact, it's much more. If I sum up over all the ij's, I get an algebra. That's not surprising because I can take the operator product expansion of an ij type operator and a jk type operator to get an ik type operator. The operator product expansion will define, up to Q exactness, defines a map, linear map from R hat ij, tensor R hat jk to R hat ik. In fact, R hat has higher operator products where we simultaneously take n boundary operators together to define an operation rho n that collapses these n boundary operators to a single operator. I'll call that rho n. This picture applies to n equals 1, in which case I take one operator to one operator, and that will just be our differential or supersymmetry operator on the chain complex. Now, in the case where the 1-0 form alpha is exact and there exists a global superpotential, there's a way of constructing these operator products. It uses something called the Webb formalism. And that was explained in detail in GMW. I can't explain the details here, but it involves pictures that look like this. And this picture has a translation into explicit equations. So when you construct the operator product, rho 2, you find that it's only associative up to Q exact terms, and the failure of associativity is governed by rho 3, and so on, just as in topological string theory. You get an A infinity algebra. So what an A infinity algebra means is the following. If I take k successive boundary operators and collapse them using rho k to a single operator, and I collapse all the remaining operators using rho n minus k plus 1 to a single operator, then I can consider all successive values, all successive sets of k successive operators, and I can sum over those, and I can sum over k with suitable signs, and the A infinity relations means I get 0. I didn't say that well. The A infinity relations is the statement that if I take all successive sets of k tuples of boundary operators and collapse them and then collapse the rest, and I sum over all of those and I sum over all k with suitable signs, I get 0. Those are the A infinity relations. And using the Webb formalism, you can show that the A infinity relations are indeed satisfied for these higher operator products that we construct rho k. In particular, taking n equals 1, rho 1 squared is 0, and so that's our chain complex, R hat ik. Now, just as there's a notion of homotopy equivalence of chain complexes, there's a notion of homotopy equivalence of A-infinity algebras. And it extends the notion of homotopy equivalence of chain complexes just by saying how the OPEs are related to each other. There's another very useful point of view on R hat. You can consider it as a category. Again, I'm still working where alpha is exact. So again, you choose a half plane, then the objects in the category are the thimbles, and the Hom spaces between the thimbles are these R hat ij's, provided the n equals 2 central charge, zij, lives in the half plane. It's just the simple complex z in degree 0 if I equals j, and it's the zero complex if zij is not in the half plane. Altogether, that defines an A-infinity category called R hat, and I'll say more about it later. Now these morphism spaces, R hat ij, or these spaces of boundary condition changing local operators, can be written in terms of the original MSW complexes we talked about, Rij. That was explained in GMW. And the formula is very elegant. We can assemble these R hat ij's into a matrix of chain complexes. So here, Eij is just the elementary matrix which has a 1 in the ith row and jth column and a 0 elsewhere. That gives me a matrix of chain complexes where the matrix element, the ij matrix element, is the chain complex R hat ij. That matrix of chain complex can be written as a product of matrix of chain complexes. We take a product over all pairs ij such the central charge is in the upper half plane. We phase order the product. And the factors we multiply are these elementary factors, which, because zij is in the upper half plane, is in the half plane H, not necessarily the upper half plane, any half plane. Because it's in that half plane, these can be considered upper triangular matrices. Now, if you take this formula and you expand out that product to write out the R hat ij in terms of the Rij's, you find the following. The summands correspond to sequences of central charges with successive vacua I, I1, I1, I2, and so on, whose phases are clockwise ordered in a half plane. So R hat ik starts its life as Rik, and so we write a picture associated with Rik that looks like that. The next term is Rij tensor Rjk, provided the central charges, Zij and similarly Zjk, are clockwise ordered. So the edges here are parallel to the central charge Zij, and so it goes. Now, I said R hat ik is a chain complex. And since I've written it as a sum of products of chain complexes, you might think, oh, the differential is just that inherited by the MSW complex. But that is actually physically wrong. It is a differential. It is mathematically a differential, but physically it is the wrong differential. And what goes wrong is that it misses important instanton effects. The instanton effects are associated with domain wall junctions, which are solutions of the zeta instanton equations with the following boundary conditions. Suppose that the phases of Zij, Zjk, and Zki are clockwise ordered. Then we could put boundary conditions on the zeta instanton equation that look like this. In the angular sector, the field phi at infinity goes to one of the vacua phi I, phi j, or phi k. On the lines, which are transition regions between the angular sectors, the lines are parallel to Zij, and on those lines, we have the soliton of type ij, phi ij of x, and similarly phi jk of x and phi ki of x. Actually, there's a subtlety here. It's not the actual soliton, it's the Euclidean boosted rotated soliton. But you can think of it as phi ij of x. In fact, 20 years ago, these kinds of domain wall junctions were actually studied in several papers, and there are even exact examples with exact solutions. Now we can take this fan of solitons, as we like to call it, phi ij, phi jk, phi ka, and we can consider them as elements in the tensor product of the MSW complexes. And then we can count numbers of solutions to the zeta instanton equations with fan boundary conditions. And that defines what we call an interior amplitude. And if we sum over all such cyclic fans of solitons, we get what I'll call RC, which is an L-infinity algebra. It was shown in GMW. And beta is a Morey-Cartan element in that L-infinity algebra. Now this interior amplitude, together with a contraction k from Rij tensor Rji to z, which exists because of CPT, defines a chain map from Rik to Rij tensor Rjk. You see, if you have a vector in Rik, you can contract it with the component in beta in Rki. What remains is a vector in Rij tensor Rjk. So it defines a map from Rik to Rij tensor Rjk. That chain map defines a new component of the differential on R hat Ik. And we can associate that component of the differential with this picture here, where you imagine that purple blob as a solution, as the domain wall. Okay, now we're ready to talk about categorical wall crossing. So if I vary parameters continuously, then the main statement is the A infinity class of the homotopy equivalence class of the A infinity category does not change. And this is actually strong enough to say how the MSW complexes Rij do change up to homotopy equivalence. We need one more notion in homological algebra. If F is a chain map from C1 to C2, then you can define a new complex called the cone on F. As a vector space, you simply take the direct sum of V2 and V1 with the grading on V1 shifted by -1. And then instead of using the naive differential with Q's along the diagonal, you use this chain map in the off diagonal position. And because it's a chain map, Q cone still squares to 0. So here's the wall crossing situation. We vary parameters so that Zij across some wall is parallel to Zjk. On one side of the wall, we have this kind of fan. We can have this kind of fan of vacua. And then there's an interior amplitude, and as I described, it defines a chain map from Ik to Ij tensor Jk. On the other side of the wall, we have a different order of fans of vacua, and that defines a similar chain map from Ij tensor Ik to Ik. So to solve we can solve the categorical wall crossing formula when alpha is exact by saying the following. The MSW complex on one side of the wall is just the cone on the chain map defined by the interior amplitude on the other side of the wall. That's the solution. That's the categorical wall crossing. This tilde means up to homotopy equivalence. Conversely, if the A infinity categories are homotopically equivalent, then the RIKs are related up to homotopy equivalence by this cone construction. So that's the solution. Here's the equation again. If I take Euler characters, which is invariant under homotopy equivalence, I get the Euler characters are related by these formulas, which are the famous Ciccati-Waffe wall crossing formulas. So we could call these Ciccati-Waffe cones. So the question then becomes, how do they generalize to the case with twisted masses? And now I realize that on my clicker, I forgot to click the time. So I have to know how much time I have. It looks like 12 minutes or 17 minutes. I think I have enough time.
Plenty of time.
So I'm going to go very quickly through this. This is the current work with Hassan. So the way the generalization to twisted masses works is the following. We define a cyclic fan of charges to be a cyclically ordered set of these homology charges with vacua I0, I1, I1, I2, but successive vacua do not have to be different. That's the new feature. We only require that the phases of the n equals 2 central charges are monotonically decreasing clockwise. So the new ingredient is that we can have fans of vacua where the vacuum doesn't change. We have fans of vacua with parallel charges. If the vacua do change, we call those irreducible fans. So then we have the old pictures. We associate this tensor product of MSW complex to this picture. We sum over all these cyclic fans of vacua, and then using the GMW web formalism, we get an L infinity algebra structure. But the new thing is we can have a fan of vacua where the vacuum does not change. You see, it could get stuck on I1, and we could have a bunch of charges gamma and 2 gamma of type I1, I1. So then we have this kind of picture where on both sides of this ray, Z gamma, this ray, we have the same vacuum, I1, I1, and then we could have several parallel central charges, Z gamma I1, I1, 2, Z sub 2 gamma I1, I1, and so on. When we have such a situation, we associate to this chain of parallel central charges graded Fock spaces on the MSW complex of periodic solitons. If I have three distinct vacua, I, J, and K, we can take a tensor product of these Fock spaces through the angular sector between gamma ij and gamma jk. And the new definition of RC, this is the innovation, is to sum over all the irreducible vertices, the irreducible fans, where we, for when the vacuum changes, we have the MSW complex of type R, and between those we have the products of Fock spaces. Our conjecture is that this has a natural L-infinity structure associated with generalized webs. It's been checked in many special cases, but not proved in general. There's a similar story on the half plane. And to simplify matters, I've chosen, again, the case of two vacua, phi I and phi j, with a rank 1 deck group. So you should think again of the peacock pattern. Then if I take a product over the peacock pattern in one half plane, I have a sum of elementary factors, and then a sum of a product of Fock spaces, and then a product of elementary factors. So if I let Fii be the product over all the Fock spaces for the periodic solitons of the correct sign of the charge, and A sub gamma ij to be the sum of the MSW complexes with charge of type ij, then we can expand out this infinite product of matrices of chain complexes and write explicit formulas for R hat II, Ji, and Ij, and so on. And we conjecture that the matrix elements of R hat are indeed morphism spaces for an A infinity category with multiplications induced from RC. And again, it's been checked in some examples. So here's the generalization of the cone formula. Here we have this product for one half plane. R hat II is given by this. And now we consider that peacock pattern, and we consider a wall crossing where Z gamma ij becomes parallel to Z gamma. Then on the other side of the wall, we write R hat prime in the reverse order, and we have similar Fock spaces and curly A's. And demanding homotopy equivalence of the A infinity categories determined by R hat and R hat prime leads to an expression of the F primes and A primes in terms of the similar quantities on the other side. So these are the equations which categorify those equations that I showed before for the BPS degeneracies. I promised you that we would categorify it, and I just fulfilled the promise. The one interesting feature here is that the R shriek is the causal dual of the complex of periodic complexes. So causal duality has played an important role in several papers in the recent years. As far as I can tell, this is a slightly different application of causal duality, but it's interesting that it's coming up in a number of contexts. Tudor Domofty summarized a number of different contexts in which causal duality comes up in quantum field theory, supersymmetric quantum field theory, in his string math talk in 2017 in Hamburg. Okay, so to close, I have about 16 minutes. I want to describe the relationship to three-dimensional indices. As I mentioned before, this is ongoing work in some discussions with Hassan, David Gaiato, and Fei Yan, and those discussions started in the context of some broader discussions where we had participation from Andy Knightsky and Tudor Domofty. So the motivation here is a recent striking conjecture by Garofalidis, Gu, and Mourinho called peacock patterns and resurgence in complex Chern-Simons theory. And what they observed, excuse me for a moment. What they observed is a relationship between the 3D index of a certain 3D supersymmetric quantum field theory, the class R theory associated with a hyperbolic knot complement, and the Stokes matrices, which are related to thimbles in complex Chern-Simons theory on the hyperbolic knot complement. What we do is we give it a natural context and state a conjecture about partial differential equations, the Kapustin-Witten equations, which implies the GGM conjecture. In fact, this conjecture, we formulated the conjecture, and just a few weeks ago we learned that exactly the same conjecture had been stated before by Viktor Mikhailov for different reasons. Not unrelated, but different reasons. Let me remind you of what the theory T of M3 is. It's just the theory obtained by reduction of the six-dimensional 2-0 theory along M3 with a suitable topological twist called the class R topological twist, as explained in these papers. If we apply to the three-dimensional theory the holomorphic topological twist described in Witten's paper on knot homology and a beautiful paper of O and Yagi, then we can identify the index with the trace over the Q cohomology of local operators at the tip of a cigar when we put the three-dimensional theory on the product of the cigar and time. Once we have a cigar, we can Kaluza-Klein reduce around the symmetry, the circular symmetry of the cigar, to get a Landau-Ginzburg theory on a half space with boundary condition B cigar. I will temporarily call it B cigar, and I will soon give it another name. Then the Q-closed local operators on the cigar times RT, sitting at the tip of the cigar, can be identified with the boundary operators for this boundary condition B cigar. And so the 3D index on T of M3 can be identified as the trace over the Hom space between the cigar boundary condition and itself of Q to the J1 and X to the J2, where J1 and J2 are global symmetry operators in the Landau-Ginzburg theory, which are obtained, induced from the operators in the three-dimensional, this 1/2 R plus J3 and E, induced from in the three-dimensional theory. Now, on the other hand, we could take the 6D20 theory on M3 times cigar times time, and again, if we Kaluza-Klein reduce on the circle, then we get five-dimensional super-Yang-Mills on M3 times the half-line R plus times time with this metric. So I'll call the coordinate along R plus Y, as is very common in this subject. As observed by Witten in a number of papers, the BPS equations, the stationary BPS equations in the 5D super Yang-Mills are just the Kapustin-Witten equations on M3 times R plus. With the boundary condition that is Y goes to 0, the Kapustin-Witten fields are given by these equations. So in the Kapustin-Witten equations are equations for a pair of a one form, phi, adjoint valued, and a connection, A. And on a three manifold, we can take the dry bind, E upper A, and the spin connection, omega A, the torsion-free connection on the tangent bundle. And we can use those to define boundary conditions on the Kapustin-Witten fields phi and A with a simple pole in Y. Those are called NOM boundary conditions. So I will rename the cigar boundary condition as the NOM boundary condition because it's intimately associated with the NOM boundary condition in the related five-dimensional super Yang-Mills theory. Now this is all related to the Chern-Simons-Landau-Ginzburg theory I mentioned before. If you take the Kapustin-Witten equations with phi y and ay equal to 0, those are nothing but the Zeta-soliton equations for the Landau-Ginzburg theory for M3 with a particular value of zeta. Well, the Kapustin-Witten equations come with a parameter t, and there's a 1-1 map between t and zeta. As we discussed before, the vacua of the Landau-Ginzburg theory are the flat connections. So we can take our NOM boundary condition, we can write it as a sum of thimble boundary conditions with Chan-Payton spaces. These Chan-Payton spaces are themselves complexes graded by fermion number, instanton number, and other global symmetries. So if we have this operator, q to the j1, x to the j2, minus 1 to the f, and we take the trace over the Hom space between the cigar and itself, then we can substitute that B cigar, which is B nom, is the sum over thimbles, and write it as a sum over the flat vacua of the characters on the Chan-Payton spaces, sandwiching the trace, the character of the Hom space between two thimbles. I can call the character of the Hom space between two thimbles S sub sigma I sigma j, S because it is indeed a Stokes matrix. It can be interpreted as the intersection of Lefschetz thimbles, That's standard in Landau-Ginzburg theory. And therefore, it can also be interpreted as the Stokes matrices for Chern-Simons symbols. So now if we specialize to a hyperbolic knot complement, we take M3 to be the knot complement in S3 of a hyperbolic knot. Then among the flat SL2C connections on MK, there's a distinguished one, sigma 1, which corresponds to the complete hyperbolic metric. Curly A is the spin connection plus I times the dry bind. And the conjecture is that the Chan-Payton space for the non-boundary condition is just Z in degree 0 for that complete hyperbolic knot and 0 otherwise. What's the evidence? Well, it gives a natural explanation of the remarkable observation of Garofalidis, Gu, and Marino. It also extends a uniqueness theorem of Mazzeo and Witten from R3 times R plus to MK times R plus. And indeed, as I mentioned before, exactly the same conjecture was made by Viktor Mikhailov for M3 times R plus, where M3 is geodesically complete and hyperbolic. And he had his own set of evidence for it. Indeed, the unique solution would just be A is the spin connection and phi is hyperbolic cotangent of Y times the dry bind. Now all this leads to an interesting generalization. If L is a colored link in M3, then following Witten, we can modify the non-boundary condition in 5-dimensional super Yang-Mills with an 't line L. In the Landau-Ginzburg context, that will correspond to a brane, which I'll call B of L. And because of the topological twist, we expect that up to homotopy equivalence, it only depends on the isotopy class of L and M3. So the final thing to say is a conjecture. If I consider the set of branes associated with these isotopy classes, this should be a sub-A infinity category of the full category of branes in our Chern-Simons Landau-Ginzburg model associated to M3. I suppress the group SL2C. We would conjecture that this category is a 3-manifold invariant, the category up to homotopy equivalence. And the A infinity algebras associated with the Hom spaces between a fixed B of L should be colored link invariants. And the main question to me is whether they are new and useful, and if so, how to compute them. So with that, let me conclude. Oh, yes, here's the conclusion. So using the framework of GMW, we derived a categorified version of the Ducati-Wafel wall crossing formula. That framework can be extended to the case with twisted masses. Here, there are qualitatively new features involving Fock spaces of periodic solitons and causal duality of complexes. The circle of ideas applied to Chern-Simons Landau-Ginzburg theory associated to a 3-manifold gives a natural framework for interpreting a recent striking conjecture of GGM, Garofalidis, Gu, and Marino, and moreover suggests potentially new colored link invariants. So with that, I'll conclude with Duomo arigato gozaimashita.
Thank you very much, Greg. Are there any questions?
Maybe I'll ask a question. I have just a minor, maybe psychological problem with the situation when you have arithmetic progressions of critical values. So that is the situation. When you pass to the covering, then the critical values, they arrange into classes, arithmetic progressions.
Correct, yeah.
Yeah. Now, if there are no arithmetic progressions, then the situation when there are 3 points on the line is considered exceptional, is considered to be on the wall.
Right.
And you don't do RIK in that case. You do
it
only if it's on one side or on the other side. And the difference.
Yes, that's right. That's right. That's right. That's why the twisted masses are a very different situation. Yes. So you're always, for those guys, you're always on a line of marginal stability. Yes. Yes. You can never get away from that line of marginal stability.
But you still consider
so our proposal is A, to work equivariantly, gamma equivariantly, and B, you have to associate to that situation the Fock spaces.
Yes. So my question is, suppose there is something in between. You still consider the gradient trajectories, which go sort of across those middle points. So there's something you don't do in the usual situation.
You mean, could we invent some mathematical formalism to deal with the marginal stability wall?
No, just how do you do? You just consider straight gradient trajectories whose images will exactly pass through the intermediate critical values.
Okay, Mikhail, maybe I'm not completely understanding your question. I'm sure it's a good one. So, so are you saying, is there a way of writing down a formalism that works on the wall of marginal stability, even in the case where there exists a superpotential?
Yes.
Okay, I do not know.
Okay.
I do not know. But you're, I mean,
okay.
Whether it's conceivable that these ideas could shed light on that situation, I really don't know.
Okay.
But you hit the nail on the head. I mean, in the case with twisted masses, you're always on a marginal stability wall because of these arithmetic projections, sequences, these of critical values up on the cover.
Okay,
so that's why it's so hard. That's why the case of twisted masses is really a very non-trivial generalization of this algebra of the infrared.
Yes.
And so our proposal is that to work gamma equivariantly. So you have to separate things, otherwise you'll just get infinity all over the place. You have to work gamma equivariantly, and then the main new thing here in the wall crossing, in the categorified wall crossing, and in the algebra of the infrared are these Fock spaces of periodic solitons.
Okay, thank you very much.
Okay, I hope I at least partially answered your question.
Thank you. Sergey Gukov, please.
Thank you, Greg, for a very nice talk. I have a quick question about the last part.
Yeah.
I wonder if this category that you introduced, it was a little too quick for me, is related to analogous category we propose to associate to a three-manifold and SL2C or other complex group with Putrov and Waffa. So Grothendieck group of that category is basically space of SL2C flat connections, or its quantum cohomology. And there was also recent work by Dongming Gun and others. In all of these works, there is a category associated to a three-manifold, and it's basically generated by critical points of complex Chern-Simons at the level of Grothendieck group.
The answer is possibly yes. I am. You are a much better expert on this subject than me. I'm approaching this from the Landau-Ginzburg point of view and the algebra of the infrared. And I'm not as familiar with a lot of the literature, including what you just mentioned, as I should be. But let me ask the following question. Are you getting somehow a Khovanov homology or some non-homology like Khovanov homology in this category? If you look at the Hom space between two objects?
That I don't know, and I'm not sure. It's as a category, this is fairly, for example, it's going to be Verlinde category for lens space, something like that.
Okay.
And yeah, but in general, it's not even MTC, or maybe not even.
Okay, so yeah.
Yeah, so I don't know.
Oh, okay, so all I can say is thank you for pointing that out, and we're going to go have a look and ask ourselves exactly your question. Is this somehow the category that you're describing in those papers?
Did you say what the Grothendieck group is again?
Yeah, Asan is on this slide. It sounds a little different.
Grothendieck group is it's also object that's been defined in several different ways. One is it's related to Skane module, and the other is it's Grothendieck group can be thought of as a perverse homology. This homology defined by Manalescu and Abu Zaid, where we basically count SL2C flat connections. Again, just in case of SL2C.
Yeah.
So in this case, the Grothendieck group will be something like Z module generated by thimbles.
Yeah, so that's why it seemed to me similar. But again, I would be curious how It is related. It's yeah. Since it's defined physically, both by our group with Pavel and Kumran and by Dongming and his group, I would suspect that it's related.
Yeah,
I don't know.
It's in the same ballpark of ideas for sure. Whether it's the same, I'm not going to, I can't answer. But thank you for pointing that out, and we're going to go have a look at that.
Okay, next, Dmitry Galatov.
Hey, Dima.
Good evening, Greg.
Nice to see you.
Nice to see you. I have kind of two questions. One is, do you think you could embed your framework with twisted masses into some kind of Fukaya-Seidel category, maybe ROPs?
Wait, sorry, Dima, I can't understand. So you say it more slowly.
Can you embed your framework with twisted masses into some Fukaya-Seidel category, like maybe ROPs Fukaya-Seidel?
Oh, yeah, probably. Again, I'm ignorant. So as you know very well, in the case without twisted masses, GMW gave a different formulation of the Fukaya-Seidel category, right? It was a different formulation, and we argued that in fact it was mathematically equivalent to Fukaya-Seidel, but the definitions are quite different. I would not be at all surprised if they have a generalization which corresponds to the case with twisted masses. Yeah, that might be, but I do not know.
I see. And
Another good question, which Hassan and I will go have a look at.
I see. And,
So if you offline, maybe you can send me some references.
okay, sure.
Thank
And another question, maybe it's more philosophical. So you can describe again, if I think of, say, grossity groups of this complexes, could I connect them to cluster variables? And if yes, it seems that on the dual side, if I mirror dual situation, it should be related to non-minuscule representations of various weights. And I thought it's a rather complicated problem. As Mina said, well, maybe
As Mina, yeah, you're referring to the work of Mina. Yeah,
and for the non-minuscule weights, it's a problem. So it seems that you automatically solve this problem.
I would be surprised if we solved a non-trivial problem. Well, okay, with mirror symmetry, it's possible that mirror symmetry did something amazing for us. But yeah, no, we haven't looked at that aspect at all. Again, a very interesting question.
It looks like we don't have further questions.
Can I ask one question, please?
Yes.
Earlier you mentioned the L-infinity algebras arising in your work. So I'm curious because L-infinity algebras tend to come with generalizations of Jacobi identities, which tend to be quite complicated because you have brackets of various size. So how do you see
by G2,
these
did you mean Gerstenhaber?
No. I mean a Jacobi identities. Jacobi.
Oh, Jacobi identities. Ah, yes. Okay. Yes, that's right. L-infinity algebra is a glorified Lie algebra. That's right. It's a Lie algebra up to homotopy. That's right. So what about it?
So can you? How do you see these Jacobi identities arising?
Oh well, in some cases, these L-infinity algebras actually are graded Lie algebras. So Hassan has worked out some special cases, I think with purely flavor charges, where in fact they are exactly graded Lie algebras. Hassan is here; he can comment. But yes, absolutely. L-infinity algebra is a special case of L-infinity algebras. It's just a Lie algebra.
Yeah, but so I think the question is, you're asking how do you actually see that these identities are satisfied in the algebras, right? In practice?
Yes.
Yeah, so that is this long paper by Greg and
Yeah.
Edward Witten and Gaeta, where they developed this entire formalism. You know, there are these web-like pictures, and looking at boundaries of those web-like pictures, you can show that that corresponds to exactly these.
Yeah, I don't know if it will help, but there's something, we define something called a convolution of webs, and then then there's something called the taut web, and the convolution of the taut web with itself is 0, and that that proves the L infinity relations. And let me mention that there's a very beautiful paper by Michal Kapranov and Kontsevich and Seibelman about the infrared formalism, where they reinterpret the webs in terms of polygons, suitable polygons. And one of the nice features of their formulation is that it suggests a generalization to higher dimensions, which to my knowledge has not really been given a physical interpretation. And I think it's one of the really interesting open problems, is to understand the physical content of the higher dimensional formulation of the web formalism. So Asan had some speculations, which he put into the end of our paper last October, but there is this really interesting open problem out there, which I don't think is very well appreciated.
Thank you.
Okay, I have one simple question. So for the case with twisted masses,
That sounds like Masahito. Where are you? Oh, yeah, there you are. Okay, yeah.
that's right. So for the case with twisted masses,
Yes,
so the potential is multi-valued, but you can go to the covering space and then make
correct.
it varied.
Yes,
So is there
correct.
that you can go to formulate the wall crossing in the covering space and connect it to downstairs?
Oh, yes, you can. I mean, the key is to work equivariantly.
I see. Maybe that's essentially what you did.
That's what we did. And yeah, I think the original versions of our draft were actually stressing that way of doing it upstairs.
I see.
But then we decided, and certainly I decided for the talk, to kind of hide that as much as possible and work downstairs. And instead of working with those vacua phi hat A and phi hat B upstairs, I decided to project everything down and just grade things by the homology class gamma ij of a path from phi I to phi j.
I see. Okay.
But there's indeed a totally equivalent formulation where you work upstairs, which in some ways is nicer because then there is a superpotential. But the main thing is you have to work gamma equivariantly.
Okay, we have 2 more raised hands. Sergey Gukov, please.
Yeah, sorry, Masahito's question just reminded me another thing I wanted to ask. Is there any connection to work of Novikov in early 80s?
You bet.
Late 70s.
My first slide said Morse-Novikov theory. So that's what I was actually describing. So the case where the one form alpha is not exact is exactly what Novikov was describing.
I see.
Yeah.
So, but then Novikov rings and things like that, there appeared on some guys that I didn't recognize, perhaps.
Well, I just formulated things in terms of periods of alpha, but the Novikov ring is the group algebra of the deck. So I have this capital gamma, this covering group gamma, and everything was graded by this gamma, but the group algebra of gamma is the Novikov ring.
I see.
So, yeah, yes, that's bang on. Yes, absolutely.
Yeah, thank you. I just wanted to clarify.
The Novikov generalization of Morse theory. Yeah. Actually, that makes a nice point. So Morse theory, the Novikov generalization of Morse theory is a non-trivial thing. So that's like adding twisted masses. Again, that makes the point that adding twisted masses is a non-trivial thing to do.
One more hand from Abiram Kidambi.
Hi, Abraham.
Hi. Just an eye question, probably just following on what Masahito just asked. So when
Yeah.
you go to covering space,
Mhm.
how do the stability conditions of the wall crossing generalize?
Right. So I defined for you the n equals 2 central charges.
Mm-hmm.
So that's the stability conditions, right?
Oh,
They're
that's
based
it.
on the
Yeah.
phases of those charges.
Mm-hmm.
So the main new thing is that instead of the difference of superpotentials Wi minus Wj. So the story that everybody knows, going back to Ciccati and Vafa, Ciccati, Fenley, and Trolligator and Vafa, is that you have Zij, which is the difference of the critical values of the superpotential, right?
Mm-hmm.
And so when Zij becomes parallel to Zjk, okay. So now you have to define new n equals 2 central charges. And those are the integrals along the homology class gamma ij that goes from phi I to phi j of that one form alpha.
I see. Okay.
So once you have the central charges, your stability conditions are the usual things.
Okay, great. Thanks.
Okay, oh, there's another hand. No, wait, any further questions?
Maybe I have one. So you call this twisted mass because it's a mirror. It, as an example, it appears as a mirror of the twisted mass. Am I right?
That's right. That's right. Yeah.
But it's more general than this.
It is more general. You're right. So as shown in your paper, you can this indeed relates to your work, Kentaro. So I'm being a little sloppy there. So twisted masses give examples of what I'm talking about, but I think the proper framework, so maybe I shouldn't call it twisted masses, but the proper framework is to work with this alpha and consider the case where alpha is not exact.
But nevertheless, you continue to call it twisted mass?
Okay, so you might have a point. Maybe that's not the best terminology. I guess
It's I mean, it is a twisted mass, right? There's a flavor symmetry, and you're gauging with respect to that. Partially gauging with flavor symmetry.
I guess
I mean, this is an example of the twisted mass, but the twisted mass is more general. That's my understanding, at least. I mean, it can come up in.
Yeah, I mean I think that's what Kentaro is saying. Twisted masses lead to this phenomenon, but it might be more general than what's usually meant by twisted masses. Perhaps we can always invent a global symmetry that we can write an external gauge field for.
I see.
Yeah, I think that's what I'm saying. So when you have a space with some non-trivial homology group, it has some topological charges, right? And gauging with respect to those, doing the twisted mass with respect to those topological charges gives you exactly a non-singly valued superpotential.
That sounds right. That sounds right. So maybe it's not more general.
Okay. Okay, thank you.
Okay, any further questions? Well then, let's thank the speaker.